kind of going through the rules of probability. So for any event, and remember an event is what you're looking for. I call it event A. So on the project, when I say event 1, 2, and 3, that's for you to decide what the events are. I'm not picking the events for you. So depending on your, each event should be your 3 circles, right? So that's how you label them 1, 2, and 3. That's completely up to you. All right. So for any event A, the probability of that event has to be greater than or equal to 0. Right. So it cannot be, basically that's just saying it cannot be a negative probability. For Axiom 2, if I add up all the probabilities in the sample space, so if I take your Venn diagram and I find a probability for every possible situation and I add them all together, it has to equal 100%. If it does not, you either miss something if it's less than 100%, or if you're over 100%, you double counted something. Axiom 3 kind of goes into a Venn diagram. It says, if I take an event and I break it into smaller pieces, if I put them all back together, I should get back to where I started. It's kind of like a puzzle, right? And that's allows us to do the given in what we call Bayes' theorem later on, is it allows us to break things apart and it can bring it all back together. Another probability one, and this is the big one, this is the one we use the most, complement. Sometimes when I am going to spell the knee, sometimes when finding my event is difficult, sometimes it's easier to find its complement. And basically to be a complement of something has to be its complete opposite. You know, so I pass this course, the complement is I fail the course, right? You can't pass and fail the course at the same time. So basically with a complement, there is no way to have an and. The two events are disjoint of each other. The additive formula is back to our set notation from earlier in the semester, where this says the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. All right, and we'll kind of get into this and go through a scenario to solve this. But this goes back to kind of what you're asking. When I'm asking to find event 1 or 2 or event 1 and 2, this is kind of the formula that you use if you do it mathematically. However, if you just pull the correct numbers out of your Venn diagram, then you don't even have to do the formula. And I'll do an example of that later where I'll show both the formula and just using the diagram. For you all that use your project, the probability of A or B or C, so this is a 3-event problem, you can see the formula gets much longer. And basically that's just saying I need to take out my, all those little pieces that they share, and then I add back in that little triangle in the very middle where they're all really connected. So to draw a figure, it's overwriting my other box. Let me move that down. Not enough room for all the boxes here. That's why you should always put your everything into one box, I guess. All right. So if we draw our Venn diagram, a little bit of a tail on that one. I erased the whole thing. Right. So this probability of A and B and C, that's that little triangle right there, right? And then all these other ones where you're subtracting out is because we kind of do a double count. Right, and that's this piece, and this piece. But what happens is when you subtract those out, you actually end up taking out this middle piece one too many times, so that's why you have to kind of add it back in. But the key to doing these is if you put values in these things, so we'll leave those all like those are ones, and we'll call this guy 3. And then my black circle will say this is a 6. And my green is, this guy is a 7. And this one is an 8. We'll call this event A. This is event B. And then we have a little C here. So remember that when we find A, we have to add the 6, the 1, the 1, and the 3. So in A is actually, let's see, 9, 10, 11. So A technically equals 11, not 6. Remember when we did this earlier in the semester, right? And then B is 7 plus 3 is 10, 11, and 12. And then C, 8, 11, 12, 13. So that's everything inside. And I could, if I really wanted to, draw a box around this. I cut my circle. And say we have 10 on the outside. My total sample space then becomes 11 plus 12. Well, we'll do this easy. 12 and 13 is 25. Plus 10 is 35. Plus 11 is 46. So my sample space is 46. And this is kind of how your Venn diagrams were in project 1. There was no probabilities. Everything was just the total, right? So now if I ask you to find the probability of A, well, that equals 11 over 46. We're good so far?
Yeah.
And if
Yes.
if I ask for the probability of A, B, and C, this little green circle, this little piece right here, right? Well, that's the little bit that's in the triangle, so that is 3 over 46. And that's kind of what I would recommend you do with your Venn diagrams, is figure out the probabilities, and then once you have the numbers, you can kind of just pull out the numbers that are specific to that. Right? So if I want the probability of A and B, this guy, I'll put an equal sign going up, that is the stuff that's in both. So there's a 1 here, but there's also this 3 here. So this is 4 over 46. I mean, they all end up being 4 over 46 just because I did my numbers, right? So if you found all of these probabilities like I'm doing here, and you add up all of them and use the formula, that works. However, the easier thing is if it wants the probability of A or B or C, you just add up all the numbers that are inside all of these, which is 36, and you put that over its total. And then I don't actually have to find all the pieces to the formula, because if I'm in A or B or C, as long as I add all these numbers just once, then that is the answer. Now, you should simplify, but I don't like to when I'm doing this, so people can see where all the numbers are coming from. Now, a quicker way than trying to add up all your numbers, well, if I am in A or B or C, which means I'm inside all the circles, its complement, its opposite, is being outside. So if I do 1 minus 10 over 46, I still get 36 over 46. And this is the kind of the key with probability, right? There's lots of different ways to do this. So it really just comes down to how you want to do it. There is more than one way. To do these things. So that's kind of how I was looking for you to do your project, because most of you that did this project, you have all the numbers in the circles and it's good to go. Now, if you know, again, you don't have to do this project just because you did the Venn diagram, and you can do this project, and if you didn't do the Venn diagram, it's just a little more work. But if you want to do this project, then it's just put in probabilities to all these numbers. Now, for an event to be disjoint or mutually exclusive, what that means is if I build another Venn diagram,
Chris, I have to say it's nice to understand what you're saying right now.
well, it's good. It means you've picked it up in previous classes.
Well, that just means I listened to you in the earlier hour and a half that I had you.
That's true. So for things to be disjoint and mutually exclusive, notice these do not connect. There is no and. That is what it means to be disjoint or mutually exclusive. I'm doing so good. My and turned out horrible. Writing with a mouse is tricky. And that's different than independent. We'll get into independent in a minute, but that's what it means to be disjoint or mutually exclusive. You have no common, right? So any questions on kind of how the laws of probability work? Let me get out of draw before I start just writing over everything.
You scroll up a little bit, that shows the really long equation. Yep. Yeah, that little one. Yeah.
I think it's pretty crystal clear. I'm on the same page with you.
Nice. The probability can be fun. The wording is what gets probability tricky. And that's what Kyle was kind of asking about the beginning with the project. You know, given is, I mean, I'm only in that spot. It does. So that's kind of the key there.
I'm just going to use my stats notes if I'm being honest.
That's fine. Yeah, because it's not like I can come up with all kinds of new stuff for probabilities, because the fact that, I mean, the rules of probabilities are the rules of probabilities.
I'm pretty sure that you use the exact same examples too.
I try to make some new ones here. So we're saying there's some new ones now.
Okay, well, I did miss the beginning part. I had a chiropractor appointment. I decided to be dumb and jump on my daughter's trampoline with her. Didn't go so well. You know, the flips she can do at 10 are not the same ones I can do at almost 30. So.
My boxes are on top of each other, trying to move them out of my way. There we go. You can come out of here, down here. Thank you. There we go. Finally, everything's moved. So, this thing called conditional probability, right? And this is kind of what Kevin was asking. I mean, sorry, Kevin. Kyle was asking about earlier. This little line here, back to my draw. That is the word given. All right, which means I changed my sample space. So before the word given, my sample space was everything, right? With the word given, I now, instead of focusing on the entire sample space, I just focus on the event that it says has happened. All right, so that's where given comes in to play. So Alicia, with her dishes, you know, she could say, given that you like plate 2, what is the probability that you liked plate 1? That is different than what is the probability that you like plate 1 and plate 2. And that's where the words mean different things. And means I'm still in the whole sample space, so I take everybody into consideration. Given means I only look at the people who liked plate 2, and out of those people who liked plate 2, who liked plate 1.
Okay, I get that.
So there's a formula for it again. So if you take your and you multiply by the probability of what you're given, then you'll get your answer. So just using our example, what is the probability of A given B? Put numbers to it from our Venn diagram, right? Well, the probability of A and B, which we found before, was 4/46, right? So 4 over 46. And I have to multiply that by my probability of B. Well, my probability of B is 12 over 46, right? So now I'm going to times this by 12 over 46. Which will give me I probably could simplify it, but I'm being lazy. Doesn't really simplify real nice, actually.
48.
So it does simplify 12 over 529 is the fraction. If I just want to put it in decimal form, well, it's very small. It's 0.023.
Wait, what's the denominator?
I got 529.
Hmm.
Mine simplified it, so I didn't do 12 because 12 times 12 is 48.
Right.
And I don't know 46 times 46, but it simplifies down to 12 over 529. So that means 4 goes into 46, so it can be simplified down. Type into a calculator. I didn't do the simplification. I was being lazy.
Hmm.
And then the multiplication rule, is it not working? Because it is 4. Yep, 4 over 46 and 12 over 46. Does 4 go into 46?
Yeah. It just
Okay.
looks weird.
Yeah, it does. I was surprised by the numbers too. The multiplication rule, all this did was move things around. So it took the and moved it to the other side, and then something's wrong with my formula here. Probability of A and B. Oh, no, my formula is wrong. I just realized it. I'm missing a big key point here. I must have got deleted it when I was doing things. Let me fix that, because like this is not making sense to me. Move that. Go to home. That should be a divide. Because these 46 were supposed to cancel. That's why it's not making any sense. So home, draw, put my little thing back in here to my given. Given. So this should be a divided by.
One-third.
Yeah, that makes way more sense. There we go. Hope if you put the right formula on your OneNotes. So this is what, 33.3%. And I should have caught this because the trick to the formula is the numerator is always the and. The denominator is whatever you're given. So if I want to do the probability of B given A, it's still probability of A and B, but then I divide by the probability of A. So that's how the formula works, is whatever is given becomes your denominator. So if I want to do the probability of B given A, this equals the probability of A and B over the probability of A. Whatever is given goes in the bottom. Which means two different things, right? This is saying I'm in B. What is the probability that I'm in A? And this is say that I am in A. What is it I'm in B? So if I go back to the cooking Venn diagram project, probability I like plate 2. Given I like plate 2, what's the probability I like 1? And this is given I like plate 1, what is the probability I like 2? So there's the differences, and the numbers will be different, right? Because I still got an A and B. That number doesn't change, so that's still 4 over 46. But this time, I'm going to divide by A, which is 11 over 46, which just becomes 4 over 11, which is 36.7%. So probabilities are kind of close, and the reason is not they won't always be. The reason is if you look at A and B, one's 11 and one's 12. It only changed by 1, but even that change by 1 still brought it up a little more than 3%. So this is the formula I like the conditional probability formula. The multiplication formula, a lot of textbooks use that formula instead. It's the same formula. All they did was move things around. So they brought B over so that A and B was by itself. So I went from a division problem to a multiplication. So that is all they did was move things around. So they're the exact same formula. I just like this one because it's nice and easy. That's our common mistake. Whatever you are given is on the bottom. Now, this other formula that says the probability of A and B equals the probability of A and the probability of B, this is how you prove if things are independent. So now we can kind of get into independence. So let me go to home, escape. Prove if independent. So this formula does not always work. You use this formula to see if things are independent of each other, right? So if we come back up here, my A and B is 4 over 46. Back to my draw here. So 4 over 46. Get rid of that box in a minute. That's my and, right? Well, the probability of A is 11 over 46. And my B is 12 over 46. And we can already see this is not going to work out for us. This equals 33. Oh, God, I can't draw threes with a mouse, I guess. 33 over 529. This is 4 over 46. Those two fractions do not equal each other. So therefore, these two events are not independent. I just got to type. This would be way easier than drawing it out. Right. So be careful with that formula. That formula doesn't mean it's always going to work. You use that formula to prove if something is independent. And since the formula did not work, A and B are not independent. And so what does independent mean? Independent means that one event has no effect on the other. Mutually exclusive means they can't happen at the same time. Independent means they have no effect on each other. And so a couple of examples of things that are independent, flipping a coin, right? If I flip a heads, that doesn't increase the probability I get a heads on the second flip. I still got a 50-50 chance of getting heads on the second flip. So therefore, the first outcome does not have an effect on the second outcome. Therefore, they are independent. And we can prove that using this formula, right? Because if I list this out using counting real quick, if I flip a coin twice, so flip a coin twice. If I list all my outcomes, I get heads and then a heads. And then I can do a heads and a tails. And then I have a tails and a heads. There we go. And then finally a heads. I'm sorry, no, a tails and a tails. So the probability of getting heads and heads, right? Getting two heads in a row. Well, there's only one of them that have two heads, and there's 4 possible scenarios. So the probability of heads and heads equals 1/4, right? So if we use our probability formula to prove they're independent, the probability of heads on the first flip equals 1/2. And oops, forgot my probability here. And then the probability of heads on the second flip equals 1/2. If I use my formula, outcome 1 times outcome 2, so 1/2 times 1/2 equals 1/4, which is what we got up here. So flipping a coin is mathematically independent. And we just talked about it just using logic. It made sense logically. Rolling dice, independent. Roulette wheel, independent. Cards, not independent. And that's why people can count cards, because they're not independent. As soon as I deal a card, the number of cards in the deck have changed. So that card has had an effect on the next card that's going to be played, because now there's less cards in the deck. So cards are not independent, and that's why people used to be able to count cards. I mean, you can still count them, but a lot of casinos changed the rules, so you don't count cards no more. Oh, there we go. There's the definition. So this guy's should be before him, but that's fine. So Command X, so we can put him above this. Yeah, I don't want to mess all that up. We'll put him here for now. All right, so any questions of all those kind of the rule? I don't make sure I'm not going too fast. Kind of went through all of that. So if we go back to what we did last class, right? And we have our little tree diagram that we used, right? And what we have to do now is, so we had culinary, nursing, and general studies, right? And then first year, second year. I don't know if I can copy this. Copy. Here. Yeah, I lost all my lines though. But that's fine. I can put them back in real quick. So remember, this is how we read a tree. We start here and then we branch off to either culinary, nursing, or general studies. And then from there, we branched off to either a first year or a second year, right? And then we're missing our first and seconds here. So then we can branch off to our first or second, and branch off here, first or second. So did we put numbers to our thing last class? We did a little bit down here, but not so much. That was just our counting, so I didn't see any. So let's put some numbers to this real quick. Because we have a small class, I'll just make them up. So say culinary we have 5 students in our class in culinary. And so 2 are in their first year, 3 are in their second. All right, and then for nursing, we'll say we have, as this program was made for nurses, so we'll make it a little heavy for nurses. We'll have 8 in their first year and 3 in their second. And general studies is always a pretty big degree. So we will do, let's see, 8, we can't go over 25. So it's 11, 16. That will go 1 over to say I open an extra slot. So we'll do 5 and 5. So that means we have a total of 26 students in the class. Now, the way we read a tree, remember, this is where we start. So when I come up here, right, and I go to this means I've gone through culinary. So this 2 actually is given I am a culinary student and I'm in my first year. So this is, given I'm a culinary student, what is the probability I'm in my first year, right? So that probability would actually be 2 over 5.
Yep.
Because it's not going to be over the total 26, right? So this is going to become 2 over 5. That looks more like a 1 than a 2. Let me just type, that'll be easier. Escape. So the probability of this event becomes 2 over 5. And then the probability of this event becomes 3 over 5. And what do you notice about those 2 numbers?
Complements.
Those are complements. They add up to 1. So, and your tree will always be that way. It has to be a complement. So this one, because I don't have any boxes yet, because I didn't build this right nicely, this becomes 8 over 5.
What?
I'm sorry, not 5, 8 over 11. 8 and 3 is 11, not 5. Thank you, Dylan. Just seeing if you're listening, that's all. Now it becomes 3 over 11. And this one is 50-50 because they're both 5s, right? So this is 5 over 10. And again, you should simplify these things, but I'm just not, just so we can see where the numbers come from when you come back and look at this. So it's really 1/2.
I really like this tree diagram. It's super duper easy to understand. I'm loving it.
Good. Some do. Some really like trees. Others don't. The key, what gets people in trouble with the tree is they forget they have to come back here.
Yeah.
And that's why, to get to these general studies students in the first year, I have to go through general studies. That's why trees are almost always conditional probability, because I am conditioning on the first branch.
Yeah.
Right? But what is interesting about this comes back to this formula right here, the multiplication rule. Because assuming these are equally likely, so we'll call them equally likely. So the probability you're in one of these 3 programs based on our tree, we'll just say is 1/3. Right? Because what I should do is go through and figure out how many people in each class. Maybe I'll do that if we actually get back into the classroom in this fall when I teach this class. But for now, we'll just, no, we won't make it culinary. Culinary is a smaller degree. So we'll say there's a 1 out of 12, 1 out of every 12 students is culinary. Nursing is definitely a big program, but not many get into it. So we'll say 1 out of 10 get into the nursing. And general studies is pretty high. So we'll say 1 out of every 3 students is general. Now I gotta make sure that, because I made up these numbers, that they don't add up more than 100. And I don't think they even come close to that. So, which I don't want them to, because there's other degrees, right? Like life sciences.
Woo.
Let's say what my plan is when I do this in class, and we have a bigger class, if I want to build a tree based on my students in class. So again, you guys are my test bed. But with the 6, I wanted to go a little bigger numbers. But that only adds up to 31 over 60, which means there's more branches, but we're not going to get into those. So we'll get rid of this 1/3. We're not going to do 1/3. Oh, that's 1/3 for them. Perfect. So the way this multiplication rule works, go away. No, I do want to draw, sorry. If I start here and I go through culinary and I go through first year, these 2 things are touching, so that means I multiply them. So 1/12 times 2/5 equals 1 over 30, if I did the math in my head right.
2 over 60, yeah. So that's the chances that if you're a student, you're a first year culinary,
This is the probability that your first year and culinary. When you multiply them, you get your and. Off a tree, only off a tree, not always and. Right? And that goes back to this formula right here, the multiplication rule. The probability of A and B equals the probability of A given B times the probability of B. And that's what we just did. Here's the probability of culinary. Here's the probability of my given. I multiply the two probabilities, and now I have my and. So this means that I'm in culinary and a first year. Well, this is the probability that given on culinary, I'm in my first year. A little bit of difference. That's where wording kind of gets tricky. But when you use a tree, these are just your probability of the events. These are your probability of given those events. And when you multiply them, you get your probability of these events as an and. Does that make sense? All right, I'm gonna keep going then. I think so.
Yes.
So now if I do nursing real quick, and I'm gonna do just first year. So nursing 1/10 times 8/11, because I'm only doing first years. Then this equals 4/55. Take 2 out of that, it becomes a 4. Take 2 out of that, it becomes a 5. Yep. So it's 4/55. And then now if I do my general studies, this is 1/3 times 5/10, which I'm going to simplify it down to be 1/2, equals 1/6. Now, if we actually built a whole tree diagram, and now I want to ask you this. I'm going to type this now so we can kind of see it. Now, I'm going to go back to home. Close. Type. If I ask you the probability you are a first year on the tree, right? Because we're not going to take into account all the first years. Well, where are my first year probabilities? Well, these guys are first year. These guys are my first year. And these guys are my first year, right? So I just have to literally add those probabilities up. So that's 1 divided by 30 plus 4 divided by 55 plus 1 divided by 6. And if I actually built this off my class, the question would be, what's the probability of your first year in my class, right? 1 divided by 30 plus 4 divided by 55 plus 1 divided by 6 gives me 3/11. And what would be interesting, unfortunately I can't do it for you all, but if we did build this off our class, that should be how many first years are actually in the class right now. But that's what's neat. If I add, once I find my ands, if I add up these three things, I find my ors. And the reason I don't have to subtract anything out, the formula says to, because when I come down here, each one of these branches are mutually exclusive, so I can't be in more than one branch. Therefore, I didn't double count anything. Therefore, I can just add everything together. And so there's the real big benefit of a tree. Once you have it built, you can answer a lot of questions using a tree diagram. And it's not too bad to build. You could take your Venn diagrams and create a tree. And I didn't do it for this project this year, but maybe I'll do it for next year. Because the two can be related, right? Any questions on the tree?
Remind me where you got the fractions for each major.
I just made them up.
Okay. All right.
Yeah. Yeah, I assumed, I just made a quick assumption that 1 out of every 12 students at the college is culinary, 1 out of 10 is nursing, and 1 out of 3 is general studies.
Okay, I get you.
Yeah. What I'll do is once I get a bigger class of like 26 students, I can actually find the probabilities them actually before class starts that day. The problem is all of you are in different degrees, so it would have just been 1 out of 1 for all of these. So that's why I wanted to make up some numbers.
I get you.
right? And a lot of people prefer tables, right? And then for some reason, the stats book talks about trees for 135 for like half a second, and then they just do everything in tables. And tables aren't bad. I mean, I've gotten a little used to them just from teaching this course now through stats, because I always like trees. So the way we could take our tree and make it into a table is if we do culinary. Did I spell that right? Yeah, I guess so. I'm going to put tabs in here. No, I'll do this, sorry. I want degree, first year, and then second year. And then we can do culinary. And then, well, how many do we say was in the first year? 2 and 3. So 2 and 3. And then we had nursing. I said it was 8 and 3. 8 and 3. And then general, wow, definitely not spelled that correctly. ERAL, there we go. Studies. We said 5 and 5. And then we can have our totals, right? So then our total here is 2 plus 5 is 15. So we have 15 in the first year and 11 in the second for a total of, no, I don't want another row. I just wanted to do total up here, but it won't let me. So back to drawing for a total of 26. And so now I can find what is the probability of culinary, I'll just call it C, and first year. Well, that is 2 people right here over 26, which then simplifies to 1 over 13. And I pray that that's what we get up here. No, we got 1 over 30. What? That should have worked out right. Why didn't I do that right?
Wait, scroll back up. 12, 25. Because that's you're doing on the tree, it's the whole student body, not just those 3 degrees, and then down bottom you're only looking at those 3 degrees.
No, it should be the same.
No, because on the top, those 3 degrees don't equal 1, but on the bottom, those 3 degrees equal 1.
Yep.
You're using 26 as your base, and up there it's whoa.
Yeah. No, you're right. Yeah, because these are all conditioned on that branch.
So you have to add in like a 4th degree, like all other degrees.
Right. Yeah, that's why. Yeah, that's right. Because this I made a total simple space. So if I would have had all the degrees in here, it would have worked out.
We can do that in the table. Just make another table for all other degrees.
Let's go on. Total. I'll call this other. So.
Yeah, I don't know.
So it won't work out because the numbers won't be the same, but we can say there's 20. I don't know. I'll say 3 more. But that's going to make our class have more than 26 people in it, too. Now we'll just leave it off. I'll play with it, figure out what I did wrong, what I was trying to show here, but it's not working as well as I wanted it. So, there we go. But then this is how you cannot use the table, right? But I can still show the conditional, right? So now if I want to do conditional, because I know this one was right, I'm back to my draw. If I want to find the probability of first given culinary, now all I care about is that row, and there is where I get the 2 over 5. As this row is the only row I care about because it's conditioned on that. There's the total of 5, and there's 2 in the first. So there's that 2/5, and then there's this. Once you scroll too far, 2/5.
Yeah.
So they should give you the same results. So I gotta go back and look and see what I screwed up somewhere. If I did, I might be just asking it the wrong way, but that is the difference between a table and a tree using the same problem. And I didn't practice this before class, as you can see. I was just going with the flow of the class or something. So perfectly here. But put things in degrees, then you start asking, so what's the probability of first year? Right, which means I take in, it's 10, 15 over 26. Right, but we got PS3 over 11, so there's something off here. And it might be just my concept. I might be mixing these two things up, which you can't compare them, but I thought you could. So I will figure that out. But this is how you're reading them different, and it's bugging me that I'm not getting the same answer. So I missed something in my lesson here. But that's how you read them, at least, because the probability of first year means it's all of these people. So I add them up. There's my total. I mean, you know, my success, and then over my total is still the 26. So the key with probability is kind of, you don't have to do a table. You don't have to do a tree. You don't have to do a Venn diagram. But if you do, it does give you a nice visual to see how to solve these. The key is remembering, and this goes back to our set notation and our truth tables, and means they have to happen together, or means I can be in one place or the other, or I could be in both. And given is kind of like the if and only if. I am only caring about those people. That's kind of the big takeaway here from probability. And I get probability wrong some of the time because it is gotta be really careful what you're asking with the words. Any questions on 7.4?
No.
All right. 7.5 is how to find expected values. And all expected value is what you expect to happen. I don't know why I have my equation. There it goes. That was bugging me. It's what you expect to happen. And all of these should be subscripts. Oh, get off draw. Which is a fancy way of saying the mean. I don't know why these didn't fix themselves. So I can fix them real quick. Insert math. There we go. Good job, math. So expected value means this is what I expect to happen. So how you use the formula, it says you take each event and multiply that event's probability, and then you add all the values up. And this is what you expect to happen in a set of events, right? So a nice easy one I like to use is heads, flipping a coin again. So we flip a coin 3 times and record the results. So I've done some of them here. I have heads, 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 tails, 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 heads, heads, tails, right? So let's kind of think about what we're missing here. So I could have heads, tails, heads. I could have tails, tails, heads. I could have tails, heads, tails. What am I missing here? Do I have a heads? No. There we go. Heads.
Tails, tails.
Heads, tails, tails.
And the complement.
And a complement. Tails, heads, heads. Nice. And the reason I know I'm done is going back to counting. I have 2 choices, heads or tails, right? So draw. And there's 3 possible outcomes. So I put, well, I don't want to call them out. Yeah, 3 possible outcomes. So therefore, 2 to the 3rd power is 8, and I have 8 different outcomes here. So I have completed my sample space, right? And that's why counting, we learned counting before probability, is so we can figure out how to count all the different ways to do things. So I like to create it in a nice table here to find expected value. So my event X is how many times I flipped heads. So in 3 flips, I can either get 0 heads, 1 head, 2 heads, or 3 heads, right? So the probability I get 0 heads, which means I get all tails, there's 1 of those out of the 8 boxes. So there's 1 out of 8, right? And 0 times anything is 0. Then the probability I get 1 head, so he has 2 heads, he has 2 heads, he has 2 heads. He has 1 head, he has 1 head, he has 1 head, he has 2. So there's 1, 2, 3. Let me get out a draw. There's 3 out of 8 ways to get 1 head, and 1 times 3/8 is still 3/8. How many have 2 heads? Well, I got 1, 2, 3. So 3/8. And 2/8 times 2 times 3/8 is 6/8. I'm not going to simplify for just a second, just so it'll make our life a lot easier in a minute. And if I add these up, 3/8 plus 3/8 plus 1/8 plus 1/8 equals 8/8. That better always happen, because you're adding up your sample space, and your sample space better equal 100% or 1, and it does in this case. So I always like to add up my P of X's to make sure they equal 1. Now, to find the expected value, I multiply these together like we did as we were going down the table, and then I add them up. Well, 0 plus 3/8 plus 6/8 plus 3/8 equals 12/8. And notice I've over 1. Expected value is not a probability. Expected value is what event you expect to happen. And 12/8 equals 3/2, or 1.5. And you think about it, if I flip a coin 3 times, it's 50-50 chance. I expect in 3 flips to get 1 or 2 heads, and we don't round expected value, so it becomes 1.5. If I flipped it 4 times, you'll see the answer actually becomes 2. Basically, I get half of my flips should be heads, and then half of 3 is 1.5. So that's why it is what you expect to happen. And that's really all it is to expected value. And expected value is a fancy way of calculating the mean. So expected value equals the mean, which equals the symbol, which I'm trying to get my 135 students to memorize, but some of them refuse. It equals the mu. This looks like a backwards 4 when I drew it there. Let me draw better. Should have more of a curvature to it. There you go. Should look more like a curve like that. A mu. And it's a Greek symbol, M, which is just a fancy symbol for the mean. But that's what expected value does. I got a curly bracket and a bracket here. There we go. So that's really, there's not much to expected value. The key to doing expected value, in my opinion, is to always build a table, because then you can do it real quick. And if you put this table in Excel, then Excel does all the calculations for you, right? And create my little table in Excel. I can actually copy this and put this in Excel. Copy. Open up Excel. And then let me change my new share whenever my Excel opens. Come on, Excel.
Still working on a new computer?
Yeah, I'm waiting for my coronavirus check. I might use that to upgrade my computer, just in case because something they've already said the summer classes are going to be on the computer. Are online. So why is my Excel not open? It says, oh, because it's already open over here. Ooh. There we go. I really made Excel angry at me here. So new share, Excel. If I paste, See if this actually pasted so I don't have to create the whole table. I did. Nice. I'm going to delete all these because I'm going to do the math. Oh, please don't tell me you pasted as a picture. No, it worked. Okay. So, delete. So here is my little table that we created before. So if I in Excel, I type equals sum, and I highlight my probabilities. And you guys can't see the Excel, right? Whoa, whoa, whoa.
Yep.
Why can't it say 0? These are numbers, Excel. Come on, work with me. Let me move this box. G4 and G7 is not equal 0. What do you think these numbers are, Excel? So, home. Where are you? ABC merged. Trying to figure out what Excel thinks these are. Oh, there it is. Just saw home. These are numbers, Excel. Number, number, number. That is so weird. Why is it doing that? Maybe copying and pasting was not the right way to go. So, one. Now it's going to put it in as a date. I know it is. Nope, there it goes. 3 over 8. 3 divided by 8. 1 divided by 8. I don't know what Excel thought those were, but I didn't think it was numbers. Now she sums to 1. And if I take that number times that number, oh, really? You don't know that's 0, 1, and 2? Holy cow. All right, so don't paste, obviously, from OneNote, because it doesn't know what I'm pasting, I guess.
This is painful to watch.
I bet it is. There's so much better packages out there besides Excel, but it's what we get for free. And it is extremely slow, too. I don't know if it's because I'm sharing it, but there's my 1.5. So the whole point at the end of this video, even though it did not go as smooth as I wanted it to, is to tell you to create your little tables when you're doing these at Excel, because then you can quickly verify they sum to 1, and then you can quickly do the mean problem and get your mean. Because if we go back to new share, here, you can see we are back, you know, it's the same thing. So that's all expected values. That's all that really goes into this problem. The key, though, is you have to understand all the concepts before, right? You must be able to find your total sample space, because that's how you're going to find the probabilities. And you have to know all the different possible outcomes you could have, which is when we go back to rules of probability. That is why, where is my, did all my stuff disappear? Oh, wow. For some reason, all the stuff I wrote on, oh, now it's just loading slow. Okay, phew. Your Venn diagram is a good way to be able to come up with all the different events, right? Your tree, or you build a table right from the get-go, and then you can find your expected values. So that's why we kind of learn it in this order, right? So first, for chapter 7, we had intro to probability, which was all the definitions, right? And so here's a nice little sample space. So if you want to do, and so we did a little bit there. Then we went into counting to find all the different ways to get our totals. And we went into some permutations and combination stuff. And then we did our rules of probability, right? Which is kind of creating these graphs. And then we finally end it with our expected value. So if I get time, I'll try to come up with a little chapter 7 activity for Wednesday's class. I'll play around with some of this stuff. If I cannot, then we'll kind of move into statistics. But we'll see what I can come up with for Wednesday, because I would like to have an activity. I at the end of the chapter kind of stuff.
Now we can still kind of do what we started kind of in class. Oh, there's a little bit more. The sum of expected values. The book talks about this, but then it doesn't do anything. I think this is more advanced probability, so I'm going to get into it very much. But just to talk about, because it's mentioned in the book. If I have the expected of two different outcomes, and I want to find the sum of them, basically it just says I don't add what the two expected numbers together. So say I got, this is 1.5 and another one's 3. I don't just add. I have to find the expected value of each and then do one.
So I'll try to come up with a scenario, but it was interesting because the book mentioned this and then it gave no problems in anything on this type of concept. So it's like a quick mention and then goes away. I didn't actually touch on the sum of expected values until I got into a more of an advanced probability class into graduate school. So this is typically higher, and we won't even get into it in the 135. It's usually a senior level or in first year of grad school advanced probability class where you start combining different populations' expected values to create a new expected value. Something you could probably do if you want to do the little book project. We're coming up with your own game. Find the expected value of a dice roll, and then expected value of coin flip, which would lead you to the expected value of your winnings. That's kind of what the book takes you through if you do the chapter 7 project out of the book versus my chapter 7, which is project is using your Venn diagram. All right, any questions? One thing I'm going to try to figure out is if I did screw up this before next class.